There will be an assignment due a week from today. We again don't have class Friday with Good Friday, and then next Monday we don't have class, being the day after Easter. So our next class is not for a week, but we will have homework due then, so I'll put that up later today on Moodle, and you should get going on it. The main thing I want to focus on today, one main thing to focus on today, but we'll bring in some other things like matrix exponentials and flows still, is to classify behaviors in the harmonic oscillator model. So let's take a look at that model again. I've got it typed into the notebook here. You can think of it either way. You can think of it as a general second order equation or a first order system. Let's think about this using parameters, constants m, b, and k. So initially you think of it like this. When you think of it as that equation, you're really thinking of it in terms of Newton's second law. That's the force, that's the mass times the acceleration. F equals ma. The force has two parts to it. This part comes from the spring, the restoring force of the spring. It's in the opposite direction as the position. So if y is positive, if the displacement is positive, it points in the negative direction. If the displacement is negative, then the restoring force points in the positive direction. And this is due to damping. That's the spring constant, that's the damping constant. That points in has the opposite sign of the velocity. So if you imagine a back and forth spring, say, and being rightward being positive and leftward being negative, when you stretch it to the right, y is positive, the restoring force is negative. If you let it go from that position, it's moving to the left, so the velocity is negative, and the damping would actually be in the positive direction. That would be a positive number when the velocity is negative. When it comes to passing through the equilibrium position and coming back this way before heading back the other way, its position y would be negative, and so the damping of the spring force, restoring force, would be in the positive direction. But if it's moving to the right, that means the velocity is positive, so this quantity would be pointing in the negative direction. Okay, that gets confusing. You have to think carefully about that, but that's a quick summary of what's going on. It's common to rewrite it in this form, where 0 is on the right-hand side. This 0 should be thought of as being up there. And it's also common to divide everything by the mass, so that the coefficient of the second derivative is 1. You can write it like that. And yet another common thing to do is to let p equal b over m and q equal k over m, so you can just think about 2 parameters rather than 3. Okay, this should all be very familiar to you. It should also be familiar to you to define the velocity to be dy dt, which I'm just writing as y prime there, to get the resulting system of equations, first order system. This is a second order equation, scalar equation. Second order because it has a second derivative. This is a first order system. First order because it only has first derivatives. System because it's a system of 2 equations. The first equation, again, is essentially a definition. We're defining the velocity to be dy dt. But once you've defined that velocity, you can say the acceleration is dv dt, and use this expression down here, replacing the dy dt with a v. And if, as is standard for us, you make little y the first variable and little v the second variable, you would want to write them in this order. It doesn't technically make a difference as far as the equation goes, but it does make a difference as far as what you decide the matrix should be. So you want to be consistent that way. Once again, p is b over m, so I can replace this b over m with a p. And q is k over m, so I can replace that k over m with that q there. And then there's the corresponding matrix. The benefit of the matrix approach now is we can just focus on the matrix. Let's go ahead and focus on that on the board. So there's our matrix. We've got these 2 unspecified parameters, p and q. Q is, again, k over m, which has to be positive, otherwise we don't have a spring, right? If k is 0, there's no spring. It's not a spring problem anymore. There's no oscillation in that case. P is B over M. In all realistic real life situations, that's positive. However, we still do think about situations where it equals 0, and we said it's an undamped case. No friction. That's not really realistic in any real life situation I know of. I mean, you can try to approximate it well if the mass is on ice and it's inside a vacuum. But there's still internal friction from a spring. I don't know how you really get rid of that. Maybe it's so small that effectively thinking of it as 0 still is a good approximation and still is worth thinking about. So we do include the case where P could be 0. By the way, what about gravity? I've said this before. If it's a horizontal back and forth motion, you don't have to worry about gravity because it's sitting on a surface and the upward force of the surface is counteracting gravity. And in the up and down situation, you actually don't have to worry about gravity either. Because, as I've put on the exam, you can attach the mass to the spring and let it move to a new equilibrium position. And essentially that motion to a new equilibrium position before you stretch it or compress it after that point cancels out the effect of gravity, essentially, and you don't have to worry about the equations. But let's go ahead and think about this in this general case. Let's find the eigenvectors, eigenvalues and eigenvectors. The eigen stuff for fun. You can use the DET notation. You can also use this pseudo absolute value notation, though it's not really an absolute value. Eigenvalues can be negative, so, and this determinant can be negative. It does not mean absolute value. It means take the determinant. Lots of negative signs there. They all end up canceling in this case. You get a positive lambda squared plus p lambda plus q. There's your characteristic polynomial. Its roots are the eigenvalues. The e-values are short. They come from the quadratic formula. Lambda equals negative p plus or minus the square root of p squared minus 4q all over 2. Right? Something you should be able to write down really quickly. What's going to happen with these eigenvalues? Well, you're going to have real eigenvalues when p squared minus 4q is greater than or equal to 0. And complex eigenvalues when p squared minus 4q is less than 0. You can write that down. Real e-values if and only if p squared minus 4q is greater than or equal to 0, which is equivalent to p squared being greater than or equal to 4q. Right? Something bothering me. Okay, I think that's right. It looks right. Stop me if something looks wrong. By the way, you can get it in terms of the three parameters, m, b, and k. P, again, is b over m. So p squared is b squared over m squared. Q is k over m. You can multiply both sides of that by m squared. That's equivalent to b squared being less than or equal to 4mk, or greater than or equal to 4mk. It's not going to be any oscillation in the real case. You're not going to get any trig functions involved because Euler's formula is not going to be needed. It's going to be a pretty highly damped case in a sense. B is big enough to make your damping big enough so that b squared is greater than or equal to 4mk, meaning you don't get any oscillation because the eigenvalues will not be complex. That's the condition. Is B big enough to make that happen? If it's not big enough, then we're going to get complex eigenvalues and you're going to get some oscillation. The complex eigenvalue case is just the opposite case. P squared minus 4q is less than 0, equivalent to p squared being less than 4q, equivalent ultimately to b squared being less than 4mk. Which is going to happen, for example, if b is 0. P is 0. When you don't have any damping. That case, actually, if p is 0, your eigenvalues are going to be purely imaginary. Because this part right there, the p will be 0, and this part will be a square root of a negative number over 2, meaning you'll get I times the square root of a positive number over 2. And again, that part will be 0, the real part will be 0. In Euler's formula, you only need to worry about the I, e to the I times something part. There will be no exponential decay term in front. What about eigenvectors? Is this worth thinking about here? Well, if I'm going to think about eigenvectors, I think I want to simplify my notation. I could let's actually do the complex case. Complex e-value case. You can also think about the real eigenvalue case. I could let alpha equal negative p over 2. The first part there from the quadratic formula. Negative p over 2. And I'm in the complex eigenvalue case, so p squared minus 4q is negative. The imaginary part of your eigenvalue will actually be square root, switch the order around inside the square root of 4q minus p squared over 2. The e-values in that case are going to be alpha plus or minus beta I. Alpha and beta are real numbers. This is called the real part of the eigenvalue, and this is called the imaginary part of the eigenvalue when we take the plus one. When it's the minus one and it's the negative, that's the imaginary part. These are both real numbers. In this complex eigenvalue case, again, p squared minus 4 4q is less than 0, which is equivalent to 4q minus p squared being greater than 0. I'm switching the order around. That's why I'm doing that. So that the beta is the imaginary part, at least the one with the plus sign. And again, we saw that you only have to worry about one of those eigenvalues. Say we worry about alpha plus beta I. Oh, where should I put it? Try to find the corresponding eigenvector. Again, I can focus on one of the equations. Negative the eigenvalue times x plus 1 times y will equal 0. Writing the eigenvalue as alpha plus beta I. There's the equation you need to solve to find the complex eigenvector. Right, I'm looking here, I'm replacing the lambda with alpha plus beta I, multiplying it times x, then adding y. And this allows us to write the complex eigenvector as 1 and then alpha plus beta I. Might as well keep going here. Let's now use Euler's formula. to expand the complex solution, which is not the solution we want real solutions. But it allows us to expand the complex solution e to the alpha plus beta I times t times this v here in terms of its real and imaginary parts. Take the real part and the imaginary part, they are both real vectors, and make a general linear combination. So now I expand this out. This is the same as e to the alpha t, which I can just leave in front, times e to the beta it, which is the same by Euler's formula as cos beta t plus I sine beta t. Multiply that times that complex vector. What's going to happen when I use that here? Well, that's just a 1 there, so on the top I'm just going to get this whole thing. I think I'll leave the e to the alpha t outside the parentheses again. What about when I multiply times that? That's the trickier one. Again, multiplying this entire thing times that. You got to think about foiling it. Again, keep the e to the alpha t out in front. Alpha, by the way, is a negative number, so this is exponential decay. Maybe I should have written alpha to be this and this, then I'd have a negative alpha up there. Alpha is a negative number. I'll stay with the way I'm doing it here, but keep in mind alpha is a negative number. Cos, what's the real part going to be? I'm going to get a cos beta t times alpha. That's going to be real, no I. I'm also going to get this part that involves the I times this part that involves the I. So I'll get beta I squared sine beta t. The I squared becomes a negative 1. So I get a minus beta times sine beta t. That's going to be the real part. Forgot my alpha here. Oh, just about out of room. What's going to go next to the I? Cos beta t times beta and sine beta t times alpha. Both of those products have an I factor. You don't get an I squared. So what goes in the parentheses there looks like it should be beta cos beta t and also plus alpha sine beta t. Hopefully I did not make any mistakes. I think it's okay. Easy to make mistakes. I'm worried that I made a mistake. Hopefully I haven't. I think I won't bother writing the rest, but again, I'll just remind you how to think about it. If you were now to find the general solution in this general case, you'd want to separate the real and imaginary parts. You'd want to think of this as being capital Y sub RE for real part. And you'd want to think about everything over here except for the I as being Y sub IM for imaginary part. It is a real vector though. It's just next to the I. It gets multiplied by the I in this complex solution. That's why we call it the imaginary part, but it is real. And then your general solution. For the original system is this. By the way, YRE and YIM will be linearly independent. So we really do get two linearly independent solutions that will generate the general solution when I write down an arbitrary linear combination of them. Okay? this vector that I circled here and this one that I kind of circled this way are going to not be multiples of each other in this two-dimensional case. Linear independence is more complicated in 3 dimensions. It's more complicated. You can't think of it in terms of vectors being multiples of each other. But in the two-dimensional case, they're linearly independent because they're not multiples of each other. Even for any fixed t, they're not multiples of each other. Question?
How did you get the eigenvector of that equation?
How did I get this
Yeah.
equation right there? I focused on the first row of a minus lambda I. Remember, the technique is to replace the lambda with what it equals, alpha plus beta I. Make that the coefficient of x. This is the coefficient of y. You get 0. You solve that for y in terms of x. The other equation would be equivalent, but more complicated looking. It wouldn't look the same at first, but eventually you'd see that it's equivalent. Okay, so listen, I think it's worth doing this just to see that you can do it for one thing, and to encourage you that, you know, maybe I'd give this on a future exam problem, probably with some guidance, that you can do it, okay? It's not quite as useful, perhaps, in the complex eigenvector case, eigenvalue case, because there are no straight line solutions. Solutions are going to spiral. They're going to be spiral sinks in this case. The real part of the eigenvalues, alpha, is a negative number. So you get an exponential decay term here. And that's why the origin's a sink, which makes good intuitive sense because we've got a harmonic oscillator with damping. The oscillations have to get smaller and smaller over time. So the alpha affects whether it's a sink or source. In this case, a sink again because alpha is negative. The beta, it does come up in the formula for the general solution, and in particular it comes up in being the coefficient of the t inside the cosine and the sine. Meaning the period, so to speak, of the solution is 2 pi over beta. Now, technically speaking, if alpha is non-zero, the solutions are not exactly periodic. It's not like an oval in the phase plane. The graph isn't purely periodic. There is an exponential decay, a spiraling toward the origin, or a decay in the amplitude. So technically speaking, in that case, the solutions are not technically periodic. But as far as their periodic part involving the cosine and the sine, the period of the oscillation, the horizontal distance between peaks, is 2 pi over beta. That's what beta affects. Beta again being this, which is a positive number here. And the frequency is 1 over the period if the reciprocal beta over 2 pi. If you were using standard units, time in seconds, then what would the units be for this frequency be? Hertz, HZ is the abbreviation. If time is not in seconds, if it's in minutes or days or millennia, yikes, then that's not hertz anymore. It would be 1 over whatever the unit of time is. But 1 over seconds is taken to be hertz. Beta itself is called the angular frequency. Beta divided by 2 pi is the frequency, the actual frequency. Don't worry about what angular frequency means right now. I'm just informing you about it. Let's think about phase planes here now. And we'll also think more about the matrix exponential and flows here. Let's go ahead and take a particular example here. Where let's go ahead and think about the complex eigenvalue case. Where did my matrices go? There's one. Okay, so I'm wanting to make this a complex eigenvalue case. By the way, the complex eigenvalue case, when you have oscillations, that's called underdamped. I'm just going to say this verbally, you can write it down. Underdamped. when you have complex eigenvalues, when your solutions oscillate either as graphs of functions of t or spiraling in the phase plane. That's called underdamped. There's not much damping, is the idea of why you call it underdamped. Damping is small enough that you still get oscillation. On the flip side, when you have real eigenvalues, when p squared minus 4q is greater than or equal to 0, and especially when it's greater than 0, technically speaking according to the book, you don't get any oscillations. That's called overdamped. Actually, when this is 0, that's called the repeated eigenvalue case, and you have one real eigenvalue in that case that's called repeated. That's sort of the boundary between two distinct real eigenvalues and two complex eigenvalues. And being the boundary, it's sort of critical, and we call it a critically damped in that case. You have two real eigenvalues. There's still no oscillation. There's no cosine or sine that comes in that case. Although the formula for the general solution ends up being a little bit more complicated. And when you read section 3.5, you'll see that extra complication come in. I'm not going to focus on that today, maybe a little next week. There's an extra complication that comes up in the repeated eigenvalue case. The main reason there's this extra complication is you can usually only find one straight line solution line. You can only find one eigenvector instead of two linearly independent ones. That's what causes the extra complication in most cases where you have a repeated eigenvalue. You can read about that. I'll talk a little bit about it next Wednesday, but for the moment, let's consider a case where we have underdamping. So I want p squared to be minus 4q to be negative. I want p squared to be less than 4q. Okay, so I'm just going to pick an arbitrary p and q where that happens. Now, if I do pick an arbitrary p and q where that happens, where p squared is less than 4q, like if p was 2 and q was 5, for example, if I just pick arbitrary thing like that, probably the algebra is not going to be so nice. Probably the eigenvalues are going to be irrational numbers. I think that's probably worth knowing. But you should know you still can handle that. Let's see if that happens. Probably it will. Yep. They involve square roots of non-perfect squares. Okay, the quadratic formula still can be used, but the square roots are not of perfect squares, so you have to deal with these irrational quantities. They can be dealt with by hand. You should be able to do them by hand, in fact. I think once in a while I put them on tests. The book does some examples. You should try some examples. You can try this example after class, in fact. So these are they're not complex numbers. There's no i's, there's no square roots of negative numbers here. But they are irrational. You can't write them as fractions of whole numbers. Their decimal expansions go on forever without a repeating pattern. They still can be handled symbolically, though. You should be able to check these eigenvalues and these corresponding eigenvectors. It's just messier. Let's try to draw the phase plane. Let's do that by hand. And we'll practice more with nullclines. Careful here, capital Y is little y, little v, not little x, little y. You want to make y horizontal and v vertical in the phase plane. The matrix, again, is 0, 1, 2, 5, corresponding to the system dy dt equals v, dv dt equals 2y plus 5, excuse me. Oh, I made a mistake, didn't I? P and Q are supposed to be negative here. So, if we want it to be something related to the harmonic oscillator, let's see, if P is negative 2, well, P is 2, but I need a negative P there. Okay, I'm getting confused on my P and Q.
Well, if your general form is minus Q, isn't that implied that Q is negative in itself?
Q and P are both positive, but you need negative signs there and there. So what did I say? P is going to be 2? Is that what I was thinking of? P squared minus 4. P squared is going to be less than 4Q. So P, I still want it to be negative, to be 2, so this is a negative 2 here. And Q is 5, so I want this to be a negative 5 there. Sorry about that. Oh, that's complex. Was I trying to do? I'm getting confused by myself here. I was trying to do the complex case, wasn't I? Wow, this is embarrassing. I'm forgetting what I was thinking about 5 minutes ago. Yeah, I was thinking about the complex case. Okay. And these numbers happen to work out nicely. Okay, let's make them work out not so nicely. Let's make this a 3 perhaps. Okay, they're complex numbers, but they still have irrational numbers involved too. You should be able to handle this too. It's not pleasant, but you should be able to handle it. Wow. This is embarrassing. All right. So let's go ahead and change this. -5, -3. Actually, I rarely get embarrassed these days. So actually, I'm not that embarrassed. I used to get embarrassed a lot more as a kid. I'm a little bit embarrassed, but not that embarrassed. People make mistakes. Okay, it just seems like I'm making a lot of them recently. There we go. I'm not going to bother editing this on YouTube either. I'll just add in some comments about my mistakes. Anyway, so there's the system. What about nullclines? In this case, the y nullcline comes from the first equation, not the second one. When is that 0? It's 0 when v is 0. In other words, the y-axis is the y nullcline. And in that case, since y is the first variable, that's when your vectors are going to be vertical. So you make a bunch of line segments. There'd be arrows from the vector field, but I'm not saying whether they're going to point up or down yet. I just know solutions are going to cross that vertically. The other nullcline is when this equals 0, which, to think about it in a standard way, I'd want to solve for v as a function of y. 3v would be -5y. v equals -5/3 y. Solve for y, for v, since v is the vertical variable. That's now a line in this picture with a slope of -5/3. About like that. I'm not going to try to be too detailed. Solutions are going to cross horizontally. These two distinct nullclines cross at the origin. The origin is the only equilibrium point. The matrix has a non-zero determinant. The determinant is 0 minus -q. The determinant is q, which is positive, because otherwise we wouldn't have a spring. How about directions for solutions? They're going to evidently spiral in toward the origin, but how do the directions go? Actually, it's good enough to just check the direction of the vector field at one point to predict what's going to happen everywhere else. For example, pick a point right around there. Imagine multiplying the matrix times that point. In this case, it's the point 1, 0, say. If you do this, you're actually going to get the first column, 0, -5. The vector in the vector field at that point, 1, 0, is going to look like that. It's going to point straight down and have a length of 5. The important point is it points straight down, so solutions have to cross this going downward over here. And then everything else is kind of forced on you. You're kind of forced to cross this way, then go up here. And the way the nullclines are situated, you see you're even forced to head toward the origin here. It is a spiral sink. All right, to save time, I'm going to, on Mathematica, in drawing this, I'm going to copy and paste some other stuff, other examples. Let's get the matrix exponential in there. This is my A down. I've got my A down here entered. That is, again, the beautiful generalization that phi sub y0 of t, defined to be e to the t times a times y0, thought of as a function of t for a fixed y0, is the unique solution to the initial value problem, dy dt equals ay, y of 0 equals y sub 0. Remember though that these are little y, little v's here. This example. So that's entered. I can take a look at it to see what it looks like. Phi, not hitting escape. Escape. There it is. pH escape of x0, y0 of t. There it is, not so pleasant looking. But there it is. It does involve trig functions, cosine, sine. It does involve exponential decay. It's all good to notice. Some more copying and pasting here. We can do the flow formula. In Mathematica, I put the t in a superscript directly above the fancy p, because in Mathematica, if you try to make it a right upward superscript, it thinks it's a power, and it's not. I'm using the other phi, okay? It's the same formula, I'm just thinking about it differently. Fancy phi t of y, I think of t as fixed. I could call it t0, I suppose. And y is the variable. It's the same formula as the other phi. Just make the y0 just a plain y now. I think of this as a linear function of y. It's a fixed matrix times y. It's a linear function of y. Just a change in perspective is all it is. I can enter this. It's going to have the exact same formula, except instead of x0 and y0, there will be x and y. There will be underscores. There it is, same formula. The x0's changed to x's, the y0's changed to y's, everything else is the same, and then you just, in your mind, think of t as fixed when you look at this. It's a linear function of x and y. What about now an animation of the flow? Let's use this one here. So technically speaking, I'm using the word flow in two ways. Flow is this family of functions, but it's also, more physically speaking, like they think about in fluid mechanics, like Professor Stein will talk about. If you take fluid mechanics, it's actually, you pretend it's an actual fluid. I didn't put the nullclines in there, but I could have. Visually, the nullcline where you've got horizontal lines would be about like this. See how my finger's crossing the place where those are have horizontal tangents? Right about like that. But it is spiraling toward the origin, and it does spiral forever and ever, though you can't tell that from the picture. And I've got the oil spill. Will the oil spill here shrink? Yes, it will. So it feels like we're applying this to oil spills. We're not really, but just for fun. It shrinks. And seemingly is turning. Is it turning or is it spiraling in a sense, it really is spiraling. I'm just not looking at it up for a long enough time to see the full spiraling. And then after time equals 0.4 there, I could go up to time equals 10, and we'd see more spiraling. And it's, well, it's doing too fast. Stop. It's going too fast to see it. It's jumping. It's, you know, not as smooth as we might like it to be. But there is a spiraling around there. Okay? So I'm not saying it's a realistic real-life flow of fluid. Again, we're pretending. Maybe we could pretend the origin really is a sink. The water's going down the sink. The oil spill is going down the sink. You could pretend that without worrying about whether it's realistic. All right, in our last 8 minutes or so, let's generalize this example. So let's copy and paste all this code and make appropriate modifications. We're going to start thinking about bifurcations again. My favorite subject in the course, pretty much. Can't avoid it. We're going to start thinking about bifurcations again. But now with systems of equations rather than rather than scalar equations. Let's change this matrix to involving an arbitrary parameter. Let's see, it probably makes more sense to let the parameter be related to the P than the Q. P is related to the damping, not the spring constant. And so what makes sense to me here is to think about letting P change, to like imagine increasing the damping. So I'm going to call this A sub P here now. And make the P a parameter here. It's there. I always have to be careful about this too. The order. So this -3, I'm going to make a negative P. Can I calculate the eigensystem for a general P? Probably, though it's not necessarily pleasant looking. But not too bad. So your eigenvalues are this and this, which could be real or complex, depending on how big P is. If P is small, they're complex. If P is small, -20 plus P squared will be negative. When P is bigger than the square root of 20, that's when that becomes positive. So maybe there's a bifurcation that occurs at P equals square root of 20. Maybe. Let's do the other stuff as well. Where should I put the P here? I suppose I could make another subscript. Like that. Make this an A sub P. Put a comma P here. Yep, it's there. It calculates it. Where should I put the P here? I think I'm going to make the P a subscript of this thing instead of putting it inside here. I think that's probably better. Maybe it doesn't matter. Well, let's see what happens if I make it a subscript of this, maybe this whole thing. See if this works. And it still seems like it's working. And down here in the manipulator, make the same kind of change. Subscript there. Do I need anything anywhere else? Doesn't look like it, though I do need it as a parameter for my manipulator. So down here after the T. Start P at 0, so no damping at first, and let P go up to bigger than the square root of 10, which is a little bit bigger than 3. So square root of 20, was that what it was?
Yep.
Which is between 4 and 5. So go up to 5. If we go up to 5, we should see the bifurcation happen. I've got 2 animation parameters. Let's watch the P change here now. That disk is not going to change. It's going to be the vector field that changes, though it's not changing very perceptibly. Did I do something wrong? Oh, I need AP for the vector plot and stream plot. y. Okay, here's the p equals 0 case, no damping. The solutions are actually exactly periodic. And actually, if we let t change, our oil spill will not get any smaller overall. I mean, it could be changing its area, I suppose. But it's definitely not getting smaller overall. It's just rotating. Though it's not a pure rotation since these are ellipses rather than circles. What happens as p changes? Watch it. If p becomes slightly positive, it's now a spiral sink, though you can't tell by looking at it. That is a spiral sink now. Doesn't look like one. It's only when p gets greater that you can tell it's a spiral sink. Like right about there, now it looks like you can probably tell it is to a slight degree. Becomes more of a spiral sink, a stronger spiral sink as p continues to increase. We add more damping. More clearly a spiral sink, the exponential decay is becoming stronger. Until we reach square root of 20, somewhere between 4 and 5, somewhere there it changes from spiraling behavior, which it still is here now, though it's hard to tell, to non-spiraling behavior. It's hard to tell where it occurs just by looking at it. Definitely when p is 5, there's non-spiraling behavior. There's two straight line solutions now, though you can't tell exactly where they are. Maybe one about like this, and one about like that. And from the other side as well. So seemingly some kind of bifurcation occurs, evidently at square root of 20. You can verify that algebraically. Now is that really a bifurcation? Last comment here. Is that really a bifurcation? It depends on your perspective. It's still a sink. It's not changing to a source or a saddle. It's changing from a spiral sink to a non-spiral sink. Is that a bifurcation or not? It depends on your perspective. If you're what's called a topologist, you would not call it a bifurcation because it's still a sink, that's all they care about. If you're more of an analyst, caring about formulas, oscillatory versus non-oscillatory behavior, then maybe you would call it a bifurcation, a change. Okay? See you in 1 week. Wow. Almost like another spring break.